All right. Okay, so next up is me, Josh Eisenberg. I'm the lead scientist at ARTI. Hold on, I'm just going to set a timer so I don't go over time. And this is work that I presented a couple weeks ago at the Narrative Understanding, Storylines, and Events workshop. A lot of my research focuses on getting computers to understand stories. People use stories to communicate, so I'm very interested in teaching computers how to understand stories. We use stories every day. Like you've probably heard more than, 20 stories over the course of this workshop so far, and we all know when the story begins and where the story ends, and we know what the events are and the plot is. But computers have a hard time doing that. Like they have a hard time doing anything that they're not explicitly taught how to do. So it's one of my goals to teach computers to understand stories, and one of the key parts of stories are events. Like a pretty basic definition of a story is a series of events that occur over time with characters enacting those events, and then there's all this structural scaffolding with details which make the story actually interesting to listen to. And stories make you think about stories from the past that you've heard, and stories from your own life. So it's kind of like a ubiquitous thing for humans, but for computers it's kind of hard to even understand the basic building blocks of stories, like what is an event, and what is plot, and what is narrative, and when does a story get interrupted. So the work today is focused on actually extracting events from stories. So what is an event? It's a thing that happens in the world, or it could even be like kind of like a state of being, like feeling sad or happy, or how something is. So the goal is to teach the computer to look at text and extract events. But I'm not interested in just any text. Like I'm working at this company called ARTI. We're a startup in Los Angeles. And we deal with dialogue. Like we make virtual characters that you could talk to on your phone, and you can have conversations with them just as you would have a conversation with a friend, so with speech. So I'm interested in training the computer to understand events in dialogue. So when I went looking through the literature, I was looking for event corpora. Most event corpora are newswire. There's time bank, mean time, and Kaggle has a corpus. There's a bunch of social media corpora, but those are different than newswire. Like social media is like Twitter, and that's very different than dialogue. And then there's a lot of event work on scientific literature, but people typically don't speak that way even at these types of conferences. So I decided I had to make my own corpus. Just to further hit the point home that dialogue is different than other types of discourse, let's compare dialogue to newswire. So back during my PhD, I built a program that can detect the point of view and the diegesis of a piece of text. So point of view is how the narrator refers to themselves. Or their self. Do they do it in first person by using first person pronouns, or third person by using third person pronouns, or second person, which is much more rare, at least in the corpora I was looking at. And diegesis is how the narrator how the narrator is related to the events in the story that they're telling. So a homodiegetic narrator is a narrator who's telling a story about themselves. Like, I went to the mall, and it was closed because of Corona. So it's something that I'm doing. Whereas a heterodiegetic narrative is a narrative that's happening to someone else. Like you're reporting things about other people. And this is more typical of newswire. So I'm comparing the corpus that I made, which I'll talk about shortly, to the Reuters newswire corpus, which is kind of a very old, ubiquitous corpus for NLP research. So first-person narrators showed up less than 1% of the time in the Reuters corpus, and less than 1% of them were homodiegetic also. Whereas in the corpus that I created, over 50% of the narrators, or the people speaking utterances, are first-person, and over 30% of them are homodiegetic. So I would like to argue that the corpus, the personal events and dialogue corpus, contains more personal events and more personalized stories because they're people who are speaking about themselves and about stories that happen to them. So I did this kind of experiment to show how different newswire is from dialogue. Like, it's something that's obvious to us, but I wanted to make it quantitative. So these are just the sources for the point of view and diegesis extractors. And crazy thing, I was able to get a patent off the features for the point of view extractor. So just to let you guys all know, if you come up with a really cool machine learning algorithm, or a really cool application of machine learning, you could try to patent the features. And that's what I did here. So now to the data set, the personal events and dialogue corpus. So it's a data set which contains 14 episodes of This American Life. This American Life is a podcast run by NPR, I think comes out of Chicago Public Media, WBEZ. And it's just stories about everyday life and also crazy life in America. So it's 14. It's excerpts from 14 episodes, and only the conversations within the episodes, because within the episodes there's even narration, which is its own type of discourse, but I was only interested when people were just talking to each other. So I combed through the episodes. The transcripts are all online and free, and I actually got permission from This American Life to open source this data with a CC BY2 license. So it's available on my website and also on Artie's website. So I'll post the link to that later. So a couple of episodes, things that they have episodes that deal with race, episodes that deal with like feminism and deal with misogyny, an episode that deals with love, an episode that deals with reality, an episode that deals with the Confederate flag, and an episode about dogs, because we all love dogs. So the data set's available here. It's open sourced. It's these 14 episodes that have been annotated for events. It's kind of like a binary classification task where each token is either labeled as an event or not an event. I could have used the TimeML annotation scheme, but it would have taken a very long time to train up the annotators, myself and Michael, who's my co-author, who actually also went to FIU and was working with me on my PhD annotation too. But we decided to make our own annotation scheme so we could get this done quickly and move on. So here's the actual episodes, the number of utterances, tokens, the number of events versus non-events. So non-events, I think, outnumbered events about 4 to 1. So the event is the minority class here. It's the more interesting thing. It's the thing that we're sifting through here. And this chart shows the inter-annotator agreements. So we did really well, you know, it was 83% on the Cohen's kappa. Anything over 80 is usually considered almost perfect. So here's just like an excerpt of an episode of The Revolution Starts at Noon. Let's zoom in. So on the top, the thing that Ira Glass says, that is narration. So we threw that out, and we only annotated the things that looked like dialogue. And yeah, so let's now talk about, like, if you're interested in what an event is and isn't, like, I'll talk about that for like about a minute or less. But I want to get more to how I taught the computer how to classify that. But events, there's some obvious events, you know, like things that happen in the world. Like if I said I went running, like the running is an event. Or I feel sad, like the sadness is an event, and also the feeling is also an event too. Like those are more states of being types of events. So there's like the obvious events that are things that actually happen, and then there's the events that represent states of being. And we decided to only annotate states of beings for animate objects. So for people or for animals, not states of being for like inanimate objects. Like if I said there's lots of mountains on the or there's lots of rocks on the mountain. Like the rocks and the mountain are both inanimate, so we wouldn't annotate those kinds of events. But if you want more information on that, check out the annotation guide and the link that I already gave, and there gives a lot more logic. And if you just look at the annotations, you'll figure out what we decided were and weren't events. So we use a number of features. We're basically just trying to get the computer to look at each word in an utterance and decide whether or not it was a event or not. So simple binary classification. I use the support vector machine. Going forward, I'll probably use something that takes to context better, but this just shows you it's a kind of simple problem, the fact that we were able to get so far only using support vector machines. So the first type of feature is verb classes. So VerbNet has verb classes. VerbNet is an ontology of verbs. There's about 200 and I think 78 different verb classes. So one of the verb classes, I'll just show you an example of the different verbs in it, like slurp, chomp, and crunch. They're all part of the chew verb class. So they're all things that involve eating. Like they have a very similar semantic meaning, you know, like the meaning's not that different between these three verbs, even though they have different lexical forms, but the meaning is basically the same. And VerbNet and the verb classes within VerbNet encapsulates this pretty well. So one of the features that we train on is what verb class a word belongs to or not. So that's 278 features right there. Part of speech tags, so which one of, I think, the 22 or 24 pen tree bang, part of speech tags based off of Stanford Core NLP, and also named entity tags from Stanford Core NLP. I thought named entity tags would kind of be a good anti-feature because things that are named entities typically aren't events. And the reason for choosing part of speech tags is verbs typically are events. Also, if you're interested to see how I extracted the verb classes, see the paper. But basically, I used it makes sense word sense disambiguation and went from WordNet senses into VerbNet classes. And semantic role labeler features, which didn't work as well as I thought they would. Semantic role labeler can extract the verb and the arguments of the verb. So Homer ate the donut, the eating is the action, Homer's the agent, the donut's the patient. I thought of knowing which words were arguments and predicates. It would help, but honestly it didn't. I might try using like a more specific parser, like parsing into FrameNet next time. Some machine learning protocols. I experimented with undersampling because there were 4 times as many non-events as there were events. I didn't want the classifier to overlearn the non-events. So I reduced the number of non-events that were shown to the classifier in learning. Remember, also we use 14-fold cross-validation. So we would remove one episode, use it for testing, and then train on the 13 other episodes. I simulated context by just showing the support vector machine, the feature vector for the previous word, the current word that we're classifying, and the next word. And we use support vector machines. Here's the results. There's a lot of numbers. You can check it out in the paper. But I just want to zoom into the best results. The F measure was about 68%, so with respect to the event class, and 88% with respect to the non-events. And the features that it used were part of speech tags, verb classes, and undersampling and trigrams, which is the context. So really cool is if you look at the 2 experiments above that, the one where it only uses undersampling or only uses trigrams, the magnitude of precision and recall flips. So this is really cool because if you're dealing with an application where you want to minimize false negatives or minimize false positives, you can do that by either using only undersampling or only trigrams. So it really depends on your application. But this is a really cool thing, distribution, and I saw this in many of the different sectors of results. Okay, and to finish up the contributions, we open source this data set. You know, it's awesome when people open source their data. Like, I want the community to use this and to train up better classifiers than mine that are able to understand dialogue better than mine, because I only got it to like 68 or 69% F measure, but I know someone else can do better. Like, I could probably do better if I had more time on it, but I'm giving you the data, so I want you to help me out. And I produce a classifier that works pretty well with part-of-speech tags and verb classes. And that is basically it. Let's see if there's any questions in YouTube. Okay, there's no questions on YouTube. Does anybody in Zoom wanna